All right. So I just posted an announcement on Canvas. If you're still confused or unsure about this bit mask business and such, there's a reference to a book that I just posted, and chapter 6 of this talks about bit flipping, so bit masks and using ands and ors to clear off pieces of a field and pull off pieces that you're interested with, and so on and so forth. So that may help, it may not. This is actually written for C, and if you're CS major and you haven't done the CS 200 level sequence yet, you're going to want to look at this stuff anyway. But it may help with some of the stuff in this class, because it's the same concept. So feel free to look at that. All right, other homework questions?
Well, number 23 asked quite a number of things.
Mm-hmm. Right, yeah, it's a 4-step.
4 shouldn't really be an issue. It's really just a matter of defining a variable.
Right, so you want to read a 2-bit number from pins 8 and 9. So how would you set up the I/O subsystem? Yeah, so set up ADCON 1, right, to be 7F. Pins 8 and 9, so go to your data sheet and look at pins 8 and 9 of the chip. That's RB0 and RB1. So you're dealing with the 2 least significant bits of port B. So you want to set those bits in tris B to be 1, and the other bits of tris B you don't care about. Well, remember, tris B is defaulted to all 1s, so you could just put all 1s into it, or you could just leave it as its default value. But make sure those 2 least significant bits of tris B are both 1s. And then show how you would copy those pins values into WReg. So, move FF port B, comma WReg, or move F port B, comma 0, right, is probably the easiest. So move F port B, comma 0. And then, is WReg's value now exactly the same as the 2-bit number you want? And the answer is absolutely not, because we only really have 2 least significant bits that are meaningful. The other 6 bits are gibberish. Right? Port B is an 8-bit register. We know that the least significant bit will correspond to RB0, and the next bit will correspond to RB1. But the next bit will correspond to RB2, which is whatever value happened to be on pin 18. We don't know what that value is. We don't know what value is on pin 17 or any of these other RB pins. So this is another question about bit masks. Right? WReg is not going to be 6 zeros followed by RB1 followed by RB0. WReg is going to be who knows, followed by RB1, followed by RB0.
I think this was explained earlier, but I just forgot. But in the move F function we just wrote, you ended it with a 0. I forgot what that 0 represents.
That says make the destination the W register. So this reads from file register port B, and it's going to write it either back into port B or into the W register. If I say comma 0, it writes it into the W register.
Oh, right.
And that's true for most byte instructions. Anything that has a destination bit, we can say comma 0. If we don't say comma 0, it defaults to comma 1, which means right into the file register. So this is copying port B to W. But the whole punchline here is that we don't know what's in these upper 6 bits. Right? I mean, we do. This is the value of RB7, this is the value of RB6, but we don't know whether those are 1s or 0s, right? And we're not interested in the value of RB7 in this question. We're not interested in the value of RB4 in this question. We're interested in the values on pins 8 and 9 being RB1 and RB0. So WReg has RB1 and RB0 in it, but it has some other stuff we don't care about, so we want to mask that out. So how do we do that? Let's AND it with a bit mask. Let's put 0s up here and 1s here, and that's going to leave us with 6 zeros, RB1 and RB0. So now WReg is a full-fledged 8-bit number, which is equal to this thing, right, where this was the least significant bit of our number, this was the most significant bit of our number. So we're just masking off the stuff we don't care about. And then you can just move FF, or move WF into first num. Does that make more sense? All right, other questions? All right, let's talk about the access bit. And this is possibly a more confusing aspect of the PIC than dealing with ports and trisses and adcons. And it's a little unfortunate because we don't really need to understand the access bit to work with this particular PIC processor successfully. The tools will take care of it for us, but in general, on other versions of the PIC and on other microprocessors, this topic is really important. Okay, so this is going to be a lot of discussion and a lot of things to think about, and not a whole lot of payoff for, you know, your homework assignments or your labs for this course. Okay, but it's a concept that cuts across architectures, it cuts across devices and product lines, and pops up in most of what you end up doing in microprocessors. It just so happens the PIC 18F1220 is simple enough that we don't have to actually worry about this, but we're going to worry about it anyway. Okay, so this is the question of the access bit. And let me start off by telling you a few things that I haven't been completely open about yet. The first is the PIC processor we're using has 256 what I'll call data file registers. These are memory locations that we can use as just plain old variables. Anytime we want to store a value or use a temporary value or make a counter, we can use one of these file registers. And their address goes from 0 to 255 in decimal. And we're always going to work in hex. And I'm always going to write 2-digit hex to remind us that these are actually 8-bit numbers. So when I want to deal with file register 0, I'll actually write it as 0x00. That's just a 0, okay? But I'm just going to try to be consistent about the format. When I want to write file register 255, I'm going to write 255 as a hexadecimal number. That's 8 ones. That's 0xFF. So this is our range of file register addresses that we deal with for just general purpose. You know, here's a temporary value to remember. I want to copy this into there, right? Where should I store there? Well, I'll pick some location 80 or 0 or something, okay? We have this whole address range. So think of this as a data bank. I'm going to call this data bank 0. And it's got 256 locations in there. Everything is 8 bits wide. Okay, so each piece of data we store in here is 8 bits. And if I want to specify any location in this data bank, all I need is 8 bits to specify the address, right? 8 bits will get me any number from 00 through FF. So it's an 8-bit address. Okay, but here's where it gets tricky. There are other versions of the PIC processor that have more than 256 file registers available. There's a version of the PIC processor that has 1024 registers available. Well, 1024, that's 4 times bigger. The addresses go from decimal 0 through 1023. Well, what does 1023 look like in binary? It's 10 ones. What does that look like in hex? It's 3FF.
Sorry, could you repeat what chip is this for again? From the 0 to 1020?
It's a fictitious chip. There are PIC chips that have this much memory in them. I don't know a particular number, but it doesn't affect our analysis. Just imagine that somebody's given you a new version of the PIC chip and it has 1024 file registers instead of just 256.
So are we going to be using this chip later on in this class, or just later on when studying EE?
Later on in life.
All right.
Alright, so I cannot just use 8 bits to specify an address because my highest location goes up to 3FF now. So I could label this 0x3FF, and let me be consistent and use 3 hex digits for all of my addresses now. So this is location 000, this is 0FF, this is 3FF. I need 10 bits in order to specify an address in this range. Well, that's a problem because if I look at my instructions and the way they're coded, I only have 8 bits available to specify a file register. Again, that works fine for us, but if we had 1024 file registers, how can we specify a file register when we only have 8 bits available? But we need 10 bits to specify the address. Okay, this is a fundamental problem. So I'm going to break my memory up into a bunch of chunks. What the PIC processor calls a bank, a data bank. And each of these banks holds 256 file registers. So this is 256 locations. This is another 256. This is another 256. This is another 256. And if I think of the addresses of these things, this first bank goes from 0 to 0FF. This goes from hex 100 to hex 1FF. Hex 200 to hex 2FF, and hex 300 to hex 3FF. Okay, all I'm doing is taking this 1024 chunk of memory and I'm breaking it into these smaller pieces that are each 256 file registers. Now I still have this question, how can I code an instruction to say I want to increment file register 600, right, which is, you know, somewhere in this bank down here, right? 600, if I code that into binary, it's got a 10-bit address. How can I say I want to increment file register 600 when my increment file register instruction only allows me to specify 8 bits for the destination, for the operand? Okay, Okay, this is a fundamental problem. And it was a big problem when Intel moved from their initial architecture, the 8080 architecture, to the 8086, or what we call x86 today. The 8080 processor was an 8-bit processor. All of the memory addresses were 16 bits. Right? The idea being 16 bits, that's 65,000 file registers. Right? Nobody could imagine needing more than that. Well, when we got to the place where we needed more than that, memory location went up to be 20 bits, but all of the instructions were designed to only use 16 bits to specify an operand. Okay, PIC processor instructions are designed to use 8 bits, but if you have more than 8 bits worth of memory, how do you specify, what location you want to work with? So we break the memory into these banks, and we have a special register called the bank select register. And if we want to access a location inside bank 2, we set the bank select register equal to 2. And now the 8 bits that we specify in our instruction give you an offset inside this bank. So if I say increment file register 80, but my bank select register is 2, I'm actually asking for location 80 inside this chunk of memory, this bank. And if I set my bank select register to 3, and I use that same increment file register 80 instruction, I'm now asking for location 80 inside this third bank of memory, this bank 3. And if I clear my bank select register and I say increment file register 80, it's just plain old location 80 in that first data bank 0. Life as it always has been. So this bank select chooses which of these blocks of 256 locations we're interested in. And these file register bits in here, these 8 bits, they're an offset within that bank. They give you a location within one of these banks. Which bank? The one specified by bank select register. So this is a banked memory approach. It's a way to still only have to code 8 bits worth of address information, but be able to access more than 2 to the 8th locations. All right, on other processors, instead of the term bank, we use the term segment. So we have a segment register that specifies which memory segment we want to work with. And when you try to access a memory location that doesn't exist, it's usually because the segment register has a bad value in it. And that results in what's called a Seg fault. So if you get Seg faults when you write C code, what you're doing is you're getting a message from the memory subsystem saying, hey, I understand what you were trying to do, but the segment you specified in the segment register is not valid. It either doesn't exist or you don't have permission to read it. And you get a Seg fault. So that's what Seg faults are. All right, back to the PIC. You okay with this? It might be a new concept, so it may take some thinking about, but okay enough to go on? Alright, so here's why this affects us with our processor, even though we only have 256 locations of data registers. So this is what the memory of the PIC processor actually looks like. Here's bank 0, goes from 00 to FF, right? And these are the 256 locations that we deal with normally. And banks 1 through banks 14 don't exist, but bank 15 does exist. Okay, bank 15 is this last chunk of 256 memory locations, and half of that bank is unused, but half of it is labeled SFR. That's the special function registers. And if you go back and you look at this table of special function registers, you see, for example, port A has the address F80. Right? That F, the first digit F, which is 15, that tells you this is in bank 15. Tri-state A is at F92. Tri-state B is at F93. And so on. W-reg is at FE8. So on our PIC processor, we know we have 256 general purpose file registers that are just locations 0 through FF. But there's also 100 some of these special function registers, and they're in a separate data bank. They're at the end of bank 15. So really, when we want to access port A, we need to do something special. If I want to say something like the following, like clear file register port A, well, port A is stored at location F80 in the PIC's memory. Okay, that's what this last table tells you. Port A, its address is F80. It's down here at the end of bank 15. Well, how do I code clearF F80? So I could say clearF, which is a 0, 1, 1, 0, 1, 0, 1, A, and then 8 Fs. Alright, so that's what the data sheet says is a clearF. So 0, 1, 1, 0, 1, 0, 1, A. I've only got 8 bits to specify a file register. F80 looks like this. And it's a 12-bit number. I can't fit that into there. So I fit in the low 8 bits like that. Well, the problem is, if instead of clearing file register F80, I wanted to clear file register 080, I'd get the same coding for F. So this is the same problem. How do I differentiate between this operand and that operand? How do I tell the processor that I mean this location instead of that location if I've only got 8 bits available? That's what the access bit does for us. So we don't have 12 bits to specify an operand. We have 8 bits, but we have one additional bit called the access bit. And that one additional bit will tell us, do we mean 80 or do we mean F80? Okay, and here's how it works. Let's go back to this diagram. So when the access bit is 0, our first 128 bytes come from bank 0, but the second 128 bytes come from bank 15. So if the access bit is 0 and I try to clear file register 80, it's going to clear file register F80. Right? It's going to jump down to this last chunk of memory. If the access bit is 1, things work exactly as if we were just in a plain old 8-bit world. And if I say clear file register 80, it's going to clear file register 80. But notice that in that case, the bank select register specifies which data bank we want in. So if I wanted to clear F80, I could move a 15 into the bank select register, set my access bit to 1, and then say clear file register 80. But that's a pain. And we use SFRs a lot, so the access bit is a convenience. If we just set the access bit to a 0, and we want to clear file register F80, we can just say clear file register 80. Okay, this does not affect us in terms of having to write code inside MPLAB. MPLAB will figure out how to set the access bit for us. Okay, the only thing it affects is if I give you a homework question, which I will on Thursday, with trying to figure out what the access bit should be. So that's question 10 that we skipped on the first homework. Alright, so I'm going to leave that at that for now, because that's a couple of different concepts layered on top of each other. But I wanted you to see this idea of banked memory, okay, because that's a common theme. And for us, we actually have two banks inside the PIC processor. We have bank 0, which is our totally general purpose memory, and we have bank 15, which is half unused and half these special function registers, port A, tris B, adcon 1, and so on. And the access bit lets us specify whether we're reading something from this first bank or from this last bank. It's slightly more complicated than that, but that's good enough for now. All right. Two more things I want to go over. One, I want to talk about bit instructions. Then I want to go through some examples of if statements, and this will set us up for the next homework, which will come out on Thursday. So another batch of instructions. There's like 5 groups of instructions. Another batch are these bit-oriented file register operations. And mainly bit clear and bit set are the ones that we're going to use the most. And so here's what these do. So suppose file register 80 contains a bunch of zeros. And suppose for some reason I wanted to change this bit 2 to be a 1. Okay, I can do that with a bit mask. I could mask it, I could OR it with a bit pattern that would force that to be a 1. But there's a separate instruction which is called bit set file register. You tell it which file register you're interested in, and you tell it which bit you want to set. Okay, after doing this bit will be a 1. So bit set file register, this is the address of the file register I'm talking about. This is the bit number in that file register that I want to set. So it changes bit 2, 0, 1, 2 to be a 1. If that bit's already a 1, it doesn't really do anything. It just leaves it as a 1. But if that bit was a 0, it changes it to a 1. And so there's 3 instructions. Bit set F turns a bit to a 1, bit clear F changes it to a 0, and bit toggle F will complement it. If it's a 1, it becomes a 0. If it's a 0, it becomes a 1. And the coding of these is slightly different. So when we write the instruction, it's say bit set file. We list the file register, comma, the bit number. And the bit number is anywhere from 0 to 7. That's 3 bits. When we code that in binary, we have the opcode. So for example, for bit set 1000, followed by the 3 bits specifying which bit you want to set. So if I wanted to set bit 0, this would be 000. If I wanted to set bit 7, this would be 111. If I wanted to set bit 2, this would be 010. So it's the binary value of the bit you want to set. Access bit will go back to ignoring, and then 8 bits for the file register. And bit clear, bit toggle are exactly the same, just different opcodes in the beginning. Is that okay with everyone? So let's just run some test code here. So take a 7F, and I'm going to move that into the W register, and then I'm going to move that into file register 80. So we've got a 7F there. And now I'm going to say bit toggle file register 80, comma 5, and our number changed to 5F. And I go back to loop and bit toggle, and it changes back to 7F. And it keeps changing between 7F and 5F. So if we look at this in binary, you can see exactly what's happening. That 5th bit keeps changing between a 1 and a 0. Okay, that's all that bit toggle does. And bit set just forces a bit to be a 1, and bit clear forces it to be a 0. But those are going to be really useful in a couple of weeks, because we're going to start doing a whole bunch of setting and clearing of individual bits in special function registers. And that's going to be our life for the last half of the course. Set this bit, clear that bit, set this bit. Okay, so bit sets and bit clears are going to be really useful. Alright, so last topic for today, which is really the start of a whole nother lecture, but let's get started on this anyway, is conditionals. So you know, you can write a bunch of statements and they execute one after another. We can say go to or branch, and we can jump back and re-execute code. And we started talking about conditional branches, branch if 0, branch if not 0. And we can use those to do looping, but we can use them more generally to do things like if-then statements. So suppose I have, you know, some variable x somewhere in memory, and somewhere in my code I want to say something like if x equals 0, then z equals 1. And let's suppose z has some value. So z is maybe at location 90 and x is at location 80. And let's write some code for this. Alright, so we want to say if x is 0, then let's set z equal to 1. So I'll have z and x here. So conditional branches, we can check to see if something is 0, we can check to see if it's not 0, if it's positive, negative, not positive, right? We have these conditional branches. So you've seen flowcharts in 120 and 121, hopefully. Here's some code. We're coming in. We get to this decision block which says is x equal to 0. And if it is, then we want to set z equal to 1. And if it's not, then we don't want to set z equal to 1. So that's all we're trying to do, right? Write some pick code that basically says if x is 0, let's do this, otherwise let's do that. There's a lot of ways we can do this. Let me show you one or two ways to do this. And if there's other ways that seem more natural to you, they're probably perfectly fine. Okay, but let me just show you some ways we could approach this. So how do we test a variable to see if it's 0 or not? Well, we have to somehow do something that updates the status bits based on the value of that variable. In this case, we want to know if x is equal to 0. So I'm going to look at my data sheet, quick reference. I'm going to look for things that affect my 0 bit, and a lot of my instructions do. In particular, move f will update my 0 bit. So if I were to say move f x, even if I don't say comma 0, right, which means just move x to itself, this will still update the 0 bit. So z is updated based on the 0 bit is updated based on the value of x. So if x is not 0, I don't want to do this increment. So I'm going to say branch if not 0 to a label that I'll call no increment. Otherwise, or let me call this not 0. Okay, move fx, which updates the 0 bit. If it's not 0, I'm going to branch to a label called not 0. Otherwise, if I didn't branch, I know x is equal to 0. So I want to set z equal to 1. Move a 1 into w, move w into z, and then here's my not 0 label. I don't know if it'll let me call a variable z. It may complain about that, but let's find out. Okay, it might work. So we'll update the z status bit based on the value of x. Branch if not 0 to not 0. So we'll skip the next part if x is not equal to 0. If we are here, then x is equal to 0, so let's set z equal to 1. So move a 1 into w, and move w into z. And we'll just put an infinite loop here at the bottom. Alright, so let's actually let's just go back up to the top. So we'll just keep running this. Uppercase, uppercase. Lowercase. Alright, so uppercase z is reserved, but we can use lowercase z. Alright, so let's go ahead and run this. We're going to move X into the W register, and we're going to say if it's not 0, jump down to not 0. Well, X, right, is location 80. It looks like it is a 0, so it should not take this branch. And we come down here and we put a 1 into W, and we put that into Z, and we just executed our code. If X is equal to 0, set Z equal to 1. There's some noise in the background. Are you talking about the sirens a minute ago? Alright, so this will do the same thing over and over again because we haven't changed X. But let's go ahead and change X. Let's give it a value of 5. And let's run this code again. So we'll move file register X into itself, and we'll say if it's not 0, branch to not 0. And this time that's what it does. It branches down to not 0, which goes back up to the top. So since X is not 0, the value of Z is never going to change. Right, Z is hex B right now. But if the value of X changes to 0, then when we execute this code, Z will get changed to a 1. Okay, so this is one way to code up this kind of if statement. And it's nothing you haven't already used, for at least a week or two. Move F is just copying X to itself, but setting the 0 bit. Branch if not 0 is really the magic, right? Which says if the last operation we did that touched the Z status bit resulted in a value that was not 0, then jump down here, right? Skip over this stuff. Otherwise, set X Z equal to 1. So we could also have done this as move F X, branch if 0 is 0. And somewhere over here we could have a section is 0 which says move a 1 into W and move W into Z. But you got to put these pieces together, right? So test the X value, and if it's 0, let's come down here to this is 0 code. Okay, so I'm going to write this a little bit incorrectly. So we're going to branch if X is equal to 0. Alright, this is not going to do exactly what we want. This moves X into itself, and it says if it's equal to 0, branch down to is 0, which says take a 1 into W, put that into Z. So this will correctly set Z equal to 1 if X is equal to 0, but what's the problem with this code as it's written?
What happens if it's not 0?
What happens if it's not 0? What's it going to do?
It will not work.
Well, what will it do? Suppose X is not 0 and I run this code.
I'll just end. Right?
It'll do something.
Will it continue to is 0?
It'll continue to is 0. Right? All that this statement says is if the result of my move operation was 0, then go ahead and take this branch. If it didn't result in 0, it's not going to take this branch. Well, what's it going to do? It's going to go on to the next instruction in memory, which is right here. So this block of code is going to get executed regardless of whether x is 0 or not. So we need to do something different here. So let's flowchart this. Is x equal to 0? And we're saying if it is, then we're going to come down to is 0. And we're going to say z equals 1. But if it's not, then we want to come somewhere other than this block of code. Right? We want to probably skip over it. So branch if 0 is 0. If we're still here, we did not branch, so x is not equal to 0. So let's go ahead and just skip here. Let's just skip this next stuff. Alright, test the value of x. If it's 0, we're going to come down here, set z equal to 1, and then we're going to end up here. Test the value of x. If it's not 0, we won't branch here. We'll execute this branch and jump down to here without doing the is 0 stuff. So this will do what we're after. So let's run that. Alright, so let's start off with everything equal to 0. We're going to move f, and if you watch your 0, well, the 0 bit's already set, so that's not interesting. We'll move f into itself. We'll say if it's 0, let's go to is 0, which it is, so we put a 1 into w, we put that into z. Z got set equal to 1 because x was 0. If instead we go through and x is not 0, okay, so watch the z bit in our status register up here. When we say move f, that z goes lowercase, that tells us the 0 bit got cleared. The result of the move was not 0. So when we say branch if 0 is 0, it's not going to take that branch. So we fall through the next instruction which says branch skip this next stuff, which what does it do? It skips that stuff and comes down here. So z did not change value because x was not 0. Alright, two kind of different approaches to doing the same thing, which is coding if x is 0, then z equals 1. Suppose we wanted to say if x is not equal to 0, then set z equal to 1. Well, I could just say branch if not 0, and I'll change my label just so it doesn't look confusing. And I'll say if x is not 0, then let's branch down to is not 0, where we set z equal to 1. Otherwise, we'll skip down to skip this stuff. So I run this and nothing happens because x is 0, and remember we're saying if x is not 0, let's go ahead and set z equal to 1. But if x changes value, and we run this code, it'll discover that x is not 0, and so it'll go down to this section of code, put a 1 into w, put that into z, z changes to 1 because x is not 0. Okay, that was about 30 minutes of discussion for, about 10 lines of code Fundamental concept. Okay, so Thursday we'll pull out a bunch of homework questions, but you can look at them already if you want from the data sheet. This next batch of questions is dealing with if statements, right? So if x equals 0, z equals z plus 1. If x equals y, z equals z plus 1. If x is not equal to y, and so on and so forth. Some of these are just go-tos, some of them are assignment statements. But it's always the same few techniques, right? So if x equals 0, just move fx, and then you can say branch if 0 or branch if not 0. If you want to know if x equals y, move x into the W register, subtract the W register from y, and then branch if 0. That will branch if x is equal to y. Why? Because saying if x equals y is the same thing as saying if x minus y is equal to 0. So we do x minus y, right? X is in the W register. We subtract the W register from y. We're doing y minus x, same thing. And then we check to see if that result was 0. So is x minus y equal to 0? The only thing to be careful of here, use the W register. Because if I just sub WFY, I'm changing the value of y. Right? I'm not only doing a conditional test, but I'm also changing y to be y minus x. So we make use of the W register there. If you want to know if x is bigger than y, that's the same thing as if x minus y is bigger than 0. So take x, subtract y, and then say branch if positive, BP. Alright, so we'll talk about the next homework on Thursday. And we'll revisit this notion of conditional branches and using this to take things like these if statements and turn them into code. And then we're going to switch gears and we're going to start digging into more of the internals of the PIC processor. And we'll have probably 1 or 2 more lectures where we're kind of on the software side. And then the second half of the course is going to be all the hardware. And it's going to involve a lot of hardware, a lot of software, but we're mainly going to be dealing with hardware aspects. So far we've mostly been dealing with assembly language, right, more of the software side, and we're going to start segueing over to dealing more with the hardware side. So that's where we'll be heading on Thursday. Alright, I will switch to my office. Catch me in there if you have lab questions. Or homework questions or want to go over any of this at all. Otherwise, I will see you on Thursday.